Okay, so here's 7.3. Essentially very similar to 7.1 and 7.2. What makes this section different is that there's going to be a word problem. You're going to have to set up a word problem first and then solve the inequality. Okay, so what I said here is application. So we're going to set up an objective function and constraints, and then we're going to solve using the method we did in 7.2. Oh, well, actually, yeah, 7.2, that's right. So here's a couple of word problems I'm going to talk to you about here. A hospital dietitian has two meal choices. One for patients on solid food that costs $2.75, and one for patients on liquids that costs $3.75. There is a maximum of 600 patients in the hospital. If the hospital has at least 100 patients on solid food and at least 100 patients on liquid, what number of each type of patient would minimize the food cost? So this is a minimization problem. So optimization, but this one's going to look for the minimum. But so when you look at what to set up for your variables and what you're looking at, you look at the questions. What number of each type of patient would minimize the food cost? So you're looking at the patients. So there is a patient that has solid food that can eat solid food, and there's a patient that has liquids that can take liquids, eat liquids, or drink liquids, I guess. So these are your variables. You let X be the number of patients on solid foods. You let Y be the number of patients on liquid foods. And as a key, look at what you're trying to minimize. You're trying to minimize food costs. So that's your objective function. So over here it says solid food costs $2.75, and liquid, the food for the patient, the one food for patient on liquids. This is the liquid food, and this is the solid food. Solid food costs $2.75. So the number of people that are on solid food is what you would need. So 275 times X is going to tell you how much it's going to cost, essentially, to feed the patient on solid food. 375 times Y is going to tell you how much it costs to feed the patient on liquids. So the cost of each is this one. If you add them up, that's a total food cost. You're trying to minimize it. So this gives you an idea of what the objective function is going to be. So whatever you're trying to optimize, in this case, food cost, that is your objective function, your Z value, your Z equation. Now your constraints here. The cost here is essentially taken care here with the objective function. So you go down to the next sentence. It says there is a maximum of 600 patients in the hospital, which means if I add the number of patients here, that can't be more than 600. So that's a constraint. So X plus Y has to be less than or equal to 600. You have a maximum of 600 patients. Then it says if the hospital has at least 100 patients on solid food and at least 100 patients on liquids, that means 100 people at least are on solids. 100 people at least are on liquids. So you have your Y greater than or equal to 100, X greater than or equal to 100. So here are constraints. So this part down we've already done. It's just taking all of this and turning it into the problem. That's the only thing different. So I'm going to do this a little faster here because we've kind of already gone over this. So if I may here, when you plug the intercept method, we plug in X to be 0 and Y to be 0 respectively, you get these two values. So this is going to be your diagonal line. When X equals 100, that means 100 for X vertical. When Y equals 100, 100 for Y vertical. If you're talking about X greater than 100, you're talking about to the right of this line. If you're talking about Y greater than 100, you're talking about above this line. Now this diagonal line, when X is 0 and Y is 0, that's clearly less than 600. So that's down here. So I'm going to shade everything under this line, to the right of this one, and above this one. So there's a little triangle that they all meet. Now this is the point 100, 100 because of where these two lines intersect. Now this line is where X equals 100 intersects X plus Y equals 600. So notice, if X is 100, Y has to be 600 minus 100, so 500. So that's where I get that point. This one, when Y is 100, notice that I plug in 100 for Y, and X is 500. So that's where I get these two coordinates. And then this one is easy because the two lines intersect here, X and Y values. So these are my 3 points. I put them into each version of the equation, and notice that my biggest answer is 2150, and my largest answer is 650. So I have essentially, I don't know that it's a maximum. Well, actually here you do because bounded, but you're looking to minimize You're looking to minimize the food costs. So this is the smallest answer. So if you only have 100 patients of each type, then the minimum cost would be 650. So keep it at the lowest amount of patients possible. Again, you can't go under 100. So this thing says, 100 is a minimum, 100 is a minimum. You can't go beyond that. You can't go less than that, which makes sense. So $650 is the minimum cost. And that's essentially how these are done. Okay, let me do, I think I have another example here. I think I did 3 examples because the toughest part essentially is set up the problem. So a canoe requires 8 hours of fabrication and a rowboat 5 hours of fabrication. Fabrication department has at least 110 hours of labor available each week. The company cannot sell more than 100 canoes. Cannot sell more than 10 canoes each week, and always sells at least 6 rowboats a week. The profit on a canoe is $400, and the profit on a rowboat is $225. How many canoes and how many rowboats should be made to maximize profit? So again, you're asking to maximize the profit. How many canoes and how many rowboats? So that kind of clues you into your variables. Your X is the number of canoes that can be made and sold, and the number of rowboats will be Y. Just made a starting off point. If you're trying to maximize profit, then your objective function is how much profit on each. So there's $400 in a profit of canoe, and there's $225 of profit of rowboat. So I put a little chart here, and this is what the way the book says it. You have essentially, let me separate this. You have the canoe you designated to be X, then the rowboats that designated to be Y. A canoe requires 8 hours of fabrication, so 8 hours for the canoe. Again, the hours of fabrication is an important detail here. It's a constraint, and a rowboat 5 hours. So you understand it says at most 100 hours, 110 hours of labor available total, 8 hours per canoe and 5 hours plus per rowboat. So it stands to reason that 8 hours per canoe plus 5 hours per rowboat is less than or equal to the 110 hours I have available of labor. And that's what this is. The objective function comes from $400 profit per canoe plus 225 profit per rowboat. And that's your z function. Now this less than or equal to 10, this greater than or equal to 6. Another constraint says here, the company cannot sell more than 10 canoes a week. Cannot go beyond 10, so 10 or less. And always sells at least 6 rowboats. So the number of rowboats is always greater than or equal to 6. So your objective function comes from this. One of your constraints comes from this one. The other two come from the word problem. So once you have this set up, which I believe to me is the toughest part of the problem, you essentially go over here and you get the graphical solution. So plugging in 0 for x and y respectively, you get essentially a decimal in the first case for x. So 13.75 value is 13.75. That's a mistake on my part because 13.75 should be the x value, not the y value. So this is 13.75. Excuse the mistake there. And the y value is 22, so this should be the point 22. It's not going to affect me that much because I really just kind of guesstimated this. Thank goodness. The line's correct. It just had these values backwards, which is not good. But hopefully you'll see that I did it. I made the correction here. So, as was said, I have this line going across. X is equal to, over here. X equals 10 is 10 here. So now, if I change essentially less than this way, y equals 6 is a horizontal line passing through the y value 6. So less than is down. So this little region. So now if this line, you take the point 0, 0, that's essentially, and in fact, I should have put this to be equal. Sorry about that. I put a 0 here and a 0 here. That's clearly less than 110, so I'm going to shade under. So where these three lines intersect is that little square there, or that little, it could be a square. Actually, that's a rectangle. Sorry. Little rectangle. So 0, 0, 0, 6, 10, 0. Now this point is where this line hits this line. So they hit it. X is 10. Jeez, that's going to throw me off there. Wow, I can't believe I did that. Not an excuse, but that's what happens is you're in a hurry. X is 10, essentially, and the Y value is 6. So this should also change. I'm embarrassed here, but let's see. So this has to be the point 10.6. So this should be 400 times 10 plus 225 times 6. Putting that into the calculator, this should be 5,350. I'm grateful that I still got where the maximum happened. I just got the wrong number. So this should be 5,350. I'm terribly sorry about that. Let me go back again here. This is the coordinate 10, 0. X is 10. This is the coordinate 0, 6. Or 6, Y value is 6, X value 10. So that's the point 10, 6, not 610. Jeez. So, again, apologize for that. I really just butchered the heck out of this problem. But I'm glad I did the video here so I can correct myself. So this is 5,350. You plug these other values, these are other corner points. You get 4,000, you get 0, you get 1,350. But this is the maximum, 5,350. So when you sell, essentially, I have this right here. When you sell, X is the number of canoes. So when you sell 10 canoes and 6 rowboats, that is where the maximum occurs. So again, jeez. I guess when I arranged it, I guess one mistake led to another mistake led to another mistake. That's kind of the way math works here. So sorry about that. When you sell 10 canoes and 6 rowboats, which means you can't go beyond 10, you have to be above 6. So if you get the bare minimum of rowboats and the maximum of canoes, you get the most profit. And that's what it's saying here. Again, sorry for that error, but hopefully this is the most important part here, the setting up. But again, this is important too. It's very important, of course. All right, let's try one more here. Let's see if I don't butcher this one. A word problem that I took here from textbook. Mike has been told each day he needs at least 16 units of vitamin A, at least 5 units of vitamin B1, and at least 20 units of vitamin C1. I'm sorry, just vitamin C, excuse me. Each brand X pill contains 8 units of vitamin A, 1 unit of vitamin B1, and 2 units of vitamin C, while each brand Y pill contains 2 units of vitamin A, 1 unit of vitamin B1, and 7 units of vitamin C. Brand X costs 15 cents a pill, brand Y costs 30 cents a pill. How many pills of each brand should he buy to minimize his daily cost? And then ultimately, what is that minimum cost? So you're trying to minimize cost. So what are you looking at? You're looking at 2 types of pills. So let X be brand X, let Y be the number of brand Y pills. That's what we did here. If you're trying to minimize a cost, then you're looking at how much each pill costs. So brand X costs 15 cents. So 15 cents times X plus 30 cents times Y. That's what you're trying to minimize or maximize. So this is your objective function. So I put the cost, I put the number of pills, and I put, because it talks about three vitamins, vitamin A, vitamin B1, and vitamin C. So vitamin A, vitamin B1, vitamin C. So you have to figure out how many types, how much of brand X you're going to get out of this. So Mike has been told he needs at least 16 units of vitamin A1, 5 units of vitamin B1, and 20 units of vitamin C. Brand X has 8 units of vitamin 1. Brand X has 8 units of vitamin 1, 1 unit of vitamin B1, and 2 units of vitamin C. While brand Y has 2 of A, 1 of B, and 7 of C. 2, 1, and 7. This part is the amount of again, of each type. So we'll get to that momentarily here. So the total amount of vitamin A that he needs is 16. So the vitamin A that comes from each one total has to be at least 16. So it stands to reason that 8 units of vitamin A1 times X times the number of per pill times the number of pills. That's how much vitamin A is going to come from the brand X pill. The amount of vitamin A is going to come from the Y pill is 2Y. That has to be at least 16. So 8X plus 2Y has to be greater than or equal to 16. That's the vitamin A. Now vitamin B, it says at least 5 units. So 1 unit of 1 unit per pill X, 1 unit per pill Y has to be at least 5 units. So that's where you get your greater than or equal to 5. Then it says what? At least 20 units of vitamin C. So at least. So it stands to reason that 2X plus 7Y has to be less than or equal to 20. And so that's where these 3 restraints are coming from. Constraints. These constraints are saying you can't have negative pills. So you have to have at least greater than or equal to 0 number of X pills, least number of Y pills greater than or equal to 0. You can't have less than that. All right, so having set this up, I think you can see 8X plus 2Y is greater than or equal to 16. 1X plus 1Y is greater than or equal to 5. 2X plus 7Y is greater than or equal to 20. And then the objective function is this. So that's where this kind of categorizes everything for us. So once you get to this, again, gonna go through this kind of quickly here. You're picking numbers, picking X to be 0, Y to be 0 for this line over here, then for the middle line here, then for the third line here. And this is about 2 and 6/7 here. So this is just arithmetic, just kind of plugging in values. So once you connect the dots of all 3, you get these 3 lines. And you get the X equals 0 and Y equals 0. So you have 5 lines essentially. Because the first 3 are greater, and here is 0, 0, everything's above the 3 lines. So everything's going this way and this way. So the upmost area where they meet, all of that is shaded. And so this is not going to have a maximum, which is good because all you're looking for is a minimum here. So this point is when Y is 8. So, well, that's actually the Y-intercept there, so that's easy. 0, 8. This is the point 10, 0. This point here is where this line X plus Y equals 5 meets 8X plus 2Y equals 6. Now, I didn't do the work here because it kind of takes a while. I don't have space for it. But I can plug in here. In this one, I can multiply by -2, cancel with Y, and solve for X. Or I can multiply by -8, cancel X, and solve for Y. In doing so, and doing the process, I get 1, 4. Where these 2 lines intersect, you get the point 3, 2. Okay, so that's something that you can kind of look into here and kind of see how their intersection. Now, earlier, I made a video, I believe, on how to get the graphical answers when you're doing graphs. That curve that kind of went down and the line that went across. If you want, you could plot this equation into your graph, but you'd have to solve for Y. And then you could plug intersection, it'll give you these points. So I get these 4 points, I plug it in for X and Y respectfully. I notice that the smallest answer is $1.05. Again, these are your 4 values, but your minimum is $1.05, which is 3 pills of brand X, 2 pills of brand Y. So buying 3 pills of brand X and 2 pills of brand Y will minimize his daily cost. So that's how many you would buy per day, and you would minimize. So this is kind of like a business model. I know it's pills, but you can also say, what if you have to hire so many people at your restaurant, and each table costs something, or the amount of food can't be less than or equal to something, it has to be at least something, or the profit has to be at no less than $1,000 a week or whatever. You can set up a business model and kind of figure out how much of each to buy to get your maximum profit. And that's really the point of this section. So that is 7.3.